Hey guys, welcome to this video. So in this video we are going to talk about the another aspect of molecular geometry that we have been dealing with. If you remember, in the past few lectures we have been talking about how do you determine molecular geometry, and we have been using the two models, that is VSEPR and valence bond theory. Now, as I discussed in the end of the last video, that we were carefully skipping two difficulties, that is when there are more than one central atoms, right? And when there is double or triple bond, what would the geometry look like? So in this particular video, we are going to talk about that. So let's start with two cases, both of which is going to involve more than one central atom and a double or a triple bond. So C2H4, now we very well know that carbon has a valency of 4, and that means its atomic number is 6. So 1s2, 2s2, 2p2. Now in C2H4, what we know is, if you write the Lewis structure, then 2 here, 2 there, 2 here, 2 there, and these are the electrons of the hydrogen, right? So by the way, I hope you remember that we follow this. We first write the Lewis structure, we count the number of electron groups, which includes bonded or lone pair, and while counting the bonded, we do not care if it's a single, if it's a double, or if it's a triple covalent bond. Then we arrange them according to VSEPR. We determine the bonded and the lone pair. Keeping in mind them, we determine the molecular geometry, and finally we determine the hybridization, right? So this is the very first step, and what we are doing is we are basically determining how many electron groups. So 1, 2, and 3, right? Now remember that this is where the bond is, right? So for this carbon, we have 3 electron groups. Now if we go to this carbon, again we have 1, we have 2, and we have 3 electron groups. Let me not include carbon here, right? So again we have 3 electron groups for each carbon. So we count the number and then we arrange them according to VSEPR. So since the electron group is 3, that means they have to be 120 degrees away from each other. So if that's the central atom, this is where the electron groups are going to be situated, that is at 120 degrees again apart from each other, and that is trigonal planar in the same plane, right? Now that is applicable to both the carbons. That means if you want to draw, then we can say that this should have been or should be the structure, each 120 degree away from each other. Now we have another thing to worry about. So as far as more than one central atom is concerned, I think we have solved our things. Now we have to talk about hybridization, right? And then we come how to play about this double bond. So if you see here, we need hybridization, right? So how many electrons are actually participating here? So let's draw 2s and 2p. So let's write 2px, that means along the x-axis, 2py and 2pz. This is 2s2. Let's fill the electrons here. Now obviously what we have to take in care here is the promotion. So let us delete this little guy from here and promote this electron right here, right? Now as we can see, according to the valence bond theory, only 3 electron groups are going to be considered. But since only 3 electron groups are going to be involved, as per this, we say only Sp2 hybridization takes place. That means upon hybridization, we have 3 Sp2 hybrid orbitals and 1 2pz orbital. Now this applies to both the carbon atoms that we are talking about, right? So according to that, let's say this is the carbon. Now this dashed line, this bold line says that this is coming out of the paper, and this is one of the bonds. So this is how the Sp2 is arranged, right? So this is 120 degrees, okay? So you have an H, right? And the same way you can do for this as well. But now you see where does a pz orbital goes, right? So this comes here. Remember, it's p, it's pure p, so it would be somewhat like this. And I hope you get the point that I am drawing this in a dotted line just as to indicate that the 4 hydrogen atoms, they are in one plane, right? They are in one plane, right? And this is above the plane, whereas this is below the plane. So you see, whereas these orbitals are colliding head on, this bond is called the sigma bond. And I hope you remember, the head on the bonds, the orbitals are oriented, the stronger the bond is. Whereas the pz orbitals, let me write this in green color just to indicate. So the pz orbitals are parallel. This type of bond is called a pi bond. Now, as you can see that the pz orbitals need to be in one plane, so the pz orbitals, they need to be in one plane. Only and only then can they align and they form the molecule, right? So this is how the hybridization works in case of multiple bonds. Now I'm gonna reduce it so that you can see all of it on one screen. So while the sigma bond is somewhat cylindrical around the axis of the bond, the pi bond is more of the cloud above and below the sigma bond. Now I want you to do the same thing for our molecule with triple bonds. So let's take the example of C2H2. Now I hope, let me stop here and give you a moment. So this is where you pause, you press the pause and you do it yourself. You do the same 5 steps for C2H2 and then we'll go ahead. So here's where I'm pressing pause. Okay, so I hope that you press the pause and you did it yourself, and let us now do the same thing. So we already know, right? 2s2, 2p2, right? That is the valence shell. But again, here in case of carbon, right? So let me put those together. So H and H. So if you count this is the Lewis pairing, right? The first step was Lewis pairing. And if you count the electron groups, so you have 1 and you have 2, right? And the same goes there as well. You have 1 and then you have 2, right? So 2 per carbon, right? Now whenever you have 2 per carbon, the symmetry is linear to place them so far apart that they have minimum repulsion from each other. That's okay as for now. So that gives you C triple bond H, H, and this is 180 degrees. Not a big deal. This was the easy part. Now let's get to the hybrid orbitals. So 2s and 2p. Now we only need 2, right? 2 orbitals. So that means you are going to be using only these orbitals, right? So let's create an sp hybridized orbital, 2 sp hybridized orbital, okay? And the remaining orbitals are going to remain just as they were before, 2py, 2pz. So I hope this makes sense that per carbon we have 2 sp orbitals. Remember, 2 is the number, okay? So if this is carbon, so you have 1 orbital right here. Remember, the shape is somewhat like this. No, somewhat like this, right? So you have 1 here and another here. Now I want to draw the same here as well. Right? So you can clearly see this is carbon, this is carbon, this is hydrogen, hydrogen. So here those are the orbitals of hydrogen. That's so far so good. Remember, this is in x direction. Now just to make things very clear, remember x, y, z, 90 degrees to each other. Okay? Okay, so now let's try to conquer these things. So y could be here, whereas z or z, as you like to pronounce, could be here. Now remember, this is z direction, whereas this one is y direction. Now the same is applicable for the other carbon as well. This is going to get a little bit messy, but bear with me and things might get better. Right? So, as you can see, now there is going to be parallel bonds between y. What are these bonds? These are going to be pi bonds, right? And bond, not bonds. Remember, orbital simply means electron could be anywhere within that purview, okay? And then you have another, right? So we can see this is the sigma bond. Sorry, let me use the red color just to have clarity. So we have 1 sigma, 1 black pi. Now I'm just saying black pi just to make things really clear, and 1 blue pi, right? So if you sum these up together, finally you have 1 sigma and 2 pi bonds in the molecule C2H2. I hope this makes sense. In the next video, we'll be talking about the molecular orbital theory and how it uses quantum physics to talk more about this.
We hope you like this video. Press subscribe, thumbs up, and stay geekly.